All right, let's talk about something that seems really straightforward but is actually full of hidden traps: distributed locking. It's all about how massive, complex systems manage to coordinate their work without descending into total chaos.
So let's put this into a real-world context. You've got all these different computers, maybe hundreds of them, all trying to work with the same shared data. How on earth do you keep them from stepping on each other's toes and making a complete mess of everything?
Okay, imagine this. You've got a big queue of documents that need to be processed, and you have a whole bunch of computers or clients all ready to jump in and do the work. The goal here is pretty simple: divide and conquer.
So let's get specific with a scenario inspired by a real developer's question. We've got 10 documents in a database. Client 1 comes along and says, "Give me 6 of them." A little later, Client 2 shows up looking for work. You'd think it would just get the 4 that are left, right? Simple. But here's the kicker. Processing these things can take a really long time, and that little detail makes this whole thing a huge headache.
This is the classic catch-22. If Client 1 puts a hard lock on those 6 documents, any other client that needs to even look at them might get stuck just waiting around. But if you don't lock them, Client 2 might accidentally grab the same documents and do the exact same expensive work. And even worse, what if Client 1 just crashes halfway through? Those documents could be trapped in limbo forever.
To try and solve this puzzle, developers often reach for a pretty specialized tool, the Distributed Lock Manager, or DLM. It's a system designed for exactly this kind of tricky coordination problem.
You can think of a DLM as kind of like the ultimate gatekeeper for your data. It runs across all the machines in your system, and its whole job is to make sure only one process at a time can get exclusive access to something important. It's like a bouncer at a very exclusive club, deciding who gets in and when.
And we're not just talking about a simple on-off switch here. These things are incredibly sophisticated. This compatibility table shows all the different kinds of locks they can handle. For instance, a DLM knows that it's totally fine for multiple clients to read the same data at once. That's a concurrent read. But the second someone needs to write, it has to get an exclusive lock and kick everybody else out. This fine-grained control is what makes a DLM feel so powerful.
So, problem solved, right? We've got this powerful, battle-tested tool that can manage access perfectly. It seems like we're all set. But here's the twist. Relying on this alone is actually a really dangerous myth, and it can lead to some absolutely catastrophic failures.
So how can this perfect solution go so horribly wrong? Well, the flaw isn't actually in the lock manager itself. It's in something much, much more fundamental about distributed systems. It's about time.
The brilliant distributed systems expert Martin Kleppmann put it perfectly. A lock in a distributed system is not like a mutex. A mutex is just a simple lock you'd use inside a single application on one computer. But the moment you add a network, with all its wild delays and uncertainties, the rules of the game just completely change.
Here is the mind-bending part you have to accept. In a distributed system, you just can't trust time. The clocks on different computers will always drift apart. Network messages can get delayed for who knows how long. So you can never ever guarantee that what one computer thinks happened first is actually what happened first from another computer's perspective.
Okay, let's watch this play out in a real disaster scenario. Client 1 asks for a lock, and the lock server says, "Sure, you got it." But right after that, the client's process just freezes. Maybe the garbage collector decides to run for a few seconds. This is called a stop-the-world pause, and to the outside world, the client just vanishes.
Now, to stop a crash client from holding a lock forever, these locks always have a built-in timer, called a lease. While client 1 is frozen solid, that lease expires. The lock service assumes it crashed and gives a brand new lock to client 2. Client 2 happily goes about its business, writes its data, and everything looks totally fine.
And here is the disaster. Client 1 finally wakes up. It has absolutely no idea its lease expired. As far as it's concerned, it still has the lock. So it just finishes what it was doing and writes its data to storage, completely blowing away the correct data that Client 2 just wrote. And that is a silent, horrifying data corruption bug. Okay, so that's a seriously scary problem. But thankfully, there's a truly elegant solution. And it doesn't require us to invent perfectly synchronized clocks or anything impossible like that. It just requires a little bit of cleverness. The solution is called a fencing token. And honestly, the best way to think about it is like getting a ticket at a deli counter. Every single time a new lock is given out, the lock service also hands out a new number, a token, that is guaranteed to be bigger than the last one.
Let's see how this completely fixes our problem.
Client 1 gets a lock and is given token number 33. Then it pauses. While it's paused, the lease expires. Client 2 comes in, gets a new lock, and is given the next token in line, number 34. Client 2 then successfully writes its data to storage, and it includes its token, 34, with that write.
Now for the magic moment. The delayed Client 1 wakes up and tries to write its data. It presents its old, stale token, number 33. But the storage service takes one look at it and says, "Nope, I've already seen a write with token 34. Yours is old news," and it rejects the request. Just like that, data corruption is averted. The fence has protected the data.
The key thing to get here is that this isn't magic, it's a team effort. The lock service has to be the one generating these always increasing tokens. The client has to be responsible enough to send its token along with every single write it makes. And, most critically, the storage system itself has to be smart enough to act as the final judge and enforce the rule.
This brings us to what might be the single most important takeaway from this entire explainer. You have to stop and really understand why you're using a lock in the first place.
You've got to ask yourself, is this lock for efficiency or is it for correctness? An efficiency lock is just to prevent you from, say, running an expensive report twice. If it fails, okay, maybe you waste a little bit of money on cloud computing or a user gets a duplicate email. It's annoying, but it's not a disaster. A correctness lock, on the other hand, is there to prevent data loss. If that lock fails, your database is now corrupt.
Look, if all you're doing is an efficiency lock, a simple, maybe even slightly buggy solution is probably fine. No big deal. But if correctness is on the line, if the integrity of your data is at stake, you absolutely, positively cannot afford to ignore the weird, squishy reality of time in distributed systems. A safety mechanism like fencing tokens isn't just a nice-to-have, it's a necessity.
And really, this whole deep dive into distributed locks points to a much bigger principle for designing reliable systems. It forces us to look at everything we build and ask a really important question. What hidden assumptions are we making? Where are we implicitly trusting that time is perfect, that networks are fast, and that processes never pause? Finding those hidden assumptions, that's the real key to building systems that don't just work, they actually endure.